In the DINICOR project, in the task 4.2, we developed a software for the review of ambulatory recorded EEG data. So here in Kempenhaeghe, we record the EEG data for 1 week. The people are free to move. They are in this area here, but they are in a flat-like environment. And for the review of this data, we developed this software where you can open an EEG file. I take this one. And you have the full functionality of a standard EEG viewer. So you can see here the electrode labels and the traces which were recorded over time. You can change the montage of the electrodes. You can also switch on and off artifact reduction and perform filtering operations. Yeah. Then what you can see here is a week of data, and usually the people here are going through this data on a 30-second or 15-second basis, and they go one monitor after the other through the data to find epileptic events for the diagnosis and maybe for preparing a surgery for epilepsy patients. We have here an automatic detection of spikes. And maybe you know from the last review, the first thing was to plot these detection results just in a list beside, and you can step through the data and see here the annotated epileptic spikes. Since the last review, we further developed this, and on the top of that we put it in spike clustering. I open another window. If I push this button here, epi spike, then this GUI pops up, and maybe I can put the raw data on the other screen. And what you can see here is the result of a clustering approach. We built a cluster based on spatial localization of the epileptic spikes in the 3D coordinates of the MR. And we assigned the labels of the next electrode to a cluster. For instance, you have the cluster F4 here. You can see that this cluster contains one epileptic spike, and this is 0.5% of all detected spikes. Here you can see the corresponding spike. And also, if you are used to read the EEG, you see immediately that this is not the correct detection, it's an artifact basically. If I go to the next cluster, F8, this one has 163 spikes. It's over 80%, and you can see an overlaid plot of these spikes here, and you immediately identify this as a correctly detected epileptic event with a maximum over this electrode F8. Because here in this time course you can also see that all the spikes, or most of the spikes detected, were close to this electrode. So what you can get out immediately from this view is that there is an epileptic source in the brain of this patient that is close to F8. Yeah. Very nice for the use by the clinicians is that if I select this cluster here, I have, let's say, all the members of the cluster, and if I identify an artifact, I can throw it away. I can clean it up manually after the automatic detection. Put away. And also very nice is that I can immediately build an average spike, and also here I can see that this is really an epileptic event was found.
Average of all cluster members, or
average of all cluster members which are selected here. Yeah, because you might want to throw away something, then you can keep the correct detections, and you see the average here. If I hit a detection in this time course in F8, this EEG plot synchronizes with that. And here is what the people in the epilepsy clinics are used to say: the signal distributed over all electrodes, and highlighted here this detected epileptic spike. Yeah, so you can have a quick check. check all your clusters and go through the data. So it's very easy to get out the clinical conclusion from this plot that the epileptic source is on F8. I can also, in addition, perform for this spike here a source calculation. So this is based on the potentials on the surface of the brain, and it calculates the sources of the activity in 3D coordinates in the brain with a bit thresholding. I can see that this is really an activity coming from the right side where the electrode T8 is located. Yeah. This is used for pre-surgical evaluations where the source localization of the spike, the source localization of the epileptic seizures and the MRE contributes to the planning of the surgery. So they resect a part of the brain and try to make the patients with that surgery seizure-free. Those two things, this source localization and this clustering approach, were developed in the DINICOR project. They are not yet certified, but we are working on that. All the other parts of the software are CE certified and also in clinical use already. After the project, we will add the certification for the spike clustering and bring it to the hospitals.
First question, how do you detect the epileptic episodes or supposed epileptic episodes at the first level with the EEG diagram? What is the technique that you use at that level?
The first thing is a set of features.
Yeah.
For the peak should be in a certain range, the slope should be in a certain range and things like that. And this is the very first level, and the second step is the clustering.
Yeah, but the first step, this is, I'm not in the field, this is a standard technique for detecting the epilepsy which is reported in the literature, or you're using something?
We are using our own, and it judges the morphology of the signal.
I see.
Yeah.
Okay. So is not a kind of pattern matching, but is extracting features and then over weighting, for instance, the features, calculating a weighted sum of features, and then having a result which is yes or no about the episodes. Is that correct?
That's correct. The classification step is involved there for saying yes or no. Yeah.
At the second layer, when you cluster, you perform a spatial clustering by using the information of the actual physical position of the electrodes. Is that correct?
Correct. Yeah.
Okay. And therefore, you say how close together are the signal in relation with the strength of the episode. Is that correct?
It's mainly a spatial clustering where you apply source localization. So you take the potentials on the surface, you calculate the generating underlying model of the activity, and then all these spikes which have their source close together end up in one cluster.
Understand.
Yeah.
And then at the third step, after having identified this and clustered, from the cluster you compute the spatial location, or from the single episode. I mean, that diagram that you shown last, is about the single episode or the cluster.
This one is only for one spike at the moment.
I understand.
For this average spike we don't have something like that, because the question is, do you average the spike and then perform this, or do you do it the other way around? So it's not clear, and we did not get out very good results with that. So we did not perform a spatial source localization for the cluster, an average or something like that.
I understand. So actually the diagram, the spatial diagram, the last one that you produce is by the episode. So if I am a clinician, it's up to me to explore different spatial distribution of the episode in order to make sure that that is exactly the region of what to intervene on.
Yes, and this is not only for one spike, you can also step through the time. You can have a look how the spikes evolves.
I see.
Can you also have that an epileptic event in one cluster creates an epileptic event in another cluster, and can you detect whether that is actually occurring by correlating in time, or are these things?
I did not understand.
Well, I'm not an expert in it, but I can imagine that an epileptic event in a single cluster is the start, of a whole epileptic chain, that you could have first an epileptic event in one spatial cluster, which triggers an epileptic event in another cluster.
Okay.
Could you have that, or?
No, because the reason is that this is only for spikes and they are very short in time. There is no evolution like a seizure. They are really short events, singular events. Yeah.